Welcome back, everyone. Welcome to this Italian afternoon session of our conference. It's my pleasure to introduce Anna Fino from Università di Torino and Florida University, and she will speak about non-Kähler manifolds via mapping tori. Please.
Okay, thank you very much. Can you hear me?
Yes.
Okay. Thank you very much to the organizer for the invitation for this wonderful conference, and also a very nice place. It's the first time in IMPA. Okay, this morning we end with Kähler geometry. The talk will be on non-Kähler geometry. And I will talk about two papers. In the first part is a joint paper with Georg Ranchero and Mischa Verbitsky. In the second part is on a paper joined with my student Beatrice Brienza and Georg Ranchero again. So let's start. We will see some construction using mapping torus of non-Kähler manifold. And in fact, the construction are coming using hyper-Kähler manifold in both cases, essentially. Let's see how. So let's start with the review, what is a mapping torus suspension. So we take a smooth manifold, we take a diffeomorphism of the manifold, and we take the quotient given by the product of M times the closed interval, 0, 1. And identification is just, okay, you identify the point. Maybe I should use this one. It's a bit big, but anyway. P0, we identify using the diffeomorphic F with F, P, and 1. This gives a manifold, which in fact has a natural fibration over the base, the circle, as 1. And the fibration is just given by the projection. You just project from the product to the closed interval, 0, 1. And the fiber is just M. The structure group of this bundle is very simple because it's just a cyclic group of diffeomorphism generated by F. There is another way to see the same quotient. We're going to use also this way, is equivalent definition. Just take again your manifold, your diffeomorphism, and consider the z action on the product of M times the real line, just given, okay, in the first element P, you just apply power of your diffeomorphism F, and in the second one, you just translate by M, by the integer. Sorry about that. No, I am doing something wrong with that. Sorry. You already so the next. Anyway, this quotient is diffeomorphic to the previous quotient. And there is a nice thing here. Simply, if you take the length 1 form on the circle and you pull back, you have a closed 1 form on your mapping torus, which is non-vanishing. By result by Tischler, it's true that a compact manifold is a mapping torus if and only if you have such closed 1 form, which is non-vanishing. This example includes, for instance, compact Néel manifold and compact Sold manifold, which are compact quotient of simply connecting importantly group or solvably group by a lattice. Okay, what type of geometry we are going to look? We already saw that Kähler geometry is quite nice. I mean, it's an intersection between complex geometry and symplectic geometry, and they have many nice topological properties. The non-Kähler geometry, in fact, we have examples. We have many examples. There are constructions, but there are not so many topological properties now, unless you look for complex dimension 2, which is complex surface, right? So the idea is to study the existence of some special Hermitian metric that involve the fundamental form. So I will just use with omega the notation about the fundamental form associated to the Hermitian metric. Sometime I will identify the metric with the form, the 1, 1, 4. And we will look at, there are many type of, let's say, weaker condition that you can put in your omega, one can look these two conditions. One is just a co-closure of omega, which is a nonlinear, essentially, condition. And another one is a DD bar closure, which is a linear condition. So already from here, you can see that the two conditions are in some sense transversal, and there are a bit, especially if you impose that your Hermitian metric is both balanced, and I will use SKT. I know that the people doesn't like so much because it's coming from physics, strong Kähler with torsion, but the metric is not Kähler, okay? I know that people like more pluriclose, but SKT is shorter, so it's, okay. We conjecture with Luigi Vezzoni, and it's still open, as far as I know, that if you take a compact complex manifold, which emit a balanced metric and another metric, which is SKT, then the manifold has to be Kähler. This has been confirmed in many cases, and we will see in the construction that I will present a different type of construction. In the first part, I will present a construction related to balanced manifold. In the second part, something related to SKT manifold. And again, we can confirm the conjecture again. We'll see in the second part the interest about the construction that I am considering is also related to the notion of what is called Bismuth-Hermitian Einstein condition. I will tell more about that. Anyway, in the non-compact case, we know now by paper by Freibert and so on that the conjecture is not true. They construct in the invariant setting, so they construct an example of two-step solvable Lie group, which emit balance and SKT metric, and it doesn't emit invariant Kähler structure. So at least compactness is necessary. Okay, I will review very quickly what is now about balance, just a short introduction. Was introduced, I think before, maybe from Alfred Gray, it was called semi-Kähler, but anyway, there is this very nice paper by Michelson where she's introduced the notion of balance metric, and the nicer thing here that everything can be detected. Yes?
Sorry, just to understand the conjecture, is it what you're trying to say is that if both metrics exist, then the balanced one is actually Kähler?
No, there is another one. There is another one, yeah, that is Kähler. So, yeah, you can have distinguished metric, and then there is another one that is Kähler. Yeah, no, yeah.
But if you have a single metric that is both
Yes,
and
bound, then it's Kähler. Then it's Kähler. And the proof is very nice proof by, it was independently shown by Alexandrov and Ivanov, and the proof is very short. In fact, it's really, yeah.
By the way, this condition of being balanced, it came up in a paper in Compte Rendu from the 50s, I think maybe by Lishnerovitz. Where he makes a very brief comment that, I mean, this doesn't do anything with it, but this is a condition that's enough to guarantee that holomorphic functions are harmonic.
Oh, yes.
We take that for granted for Kähler metrics, but actually what you're using is it's balanced.
Okay, I see. I didn't know about that. Good to know. Thank you. Yes. Lishnerovich. Very good. Okay, so that condition for balance, it makes sense, of course, only for n, complex dimension n bigger than 2, because for n equal to 2, you have the Kähler condition. There is this nice characterization by Guduchon in terms of a smooth function with compass value, in terms of the free Laplacian. But the nicer thing here is this characterization by Michelson in terms of currents. She showed that the compact complex manifold has a balance metric if and only if it has no positive currents of degree 1, which are component of the boundary. So it cannot be something like d s bar plus d bar s. This is nice because we will use later this characterization again in our construction. But for instance, one can show the Calabi-Ekman manifold, product of two odd-dimensional spheres, cannot have any balance metric. But this is specifically for the complex structure that you have in Calabi-Ekman manifold. So you're using the projection over the product of complex projective space is holomorphic, so for that case. For instance, it's not known if S3 cross S3 has balance metric at all. Okay, example, twistor space that was mentioned already this morning. And the nice thing about balance that is preserved by bimeromorphism. That was shown by Alessandrini and Bassanelli. And for instance, that means that in the class of balance manifold, you have the Moyezon manifold and also the Fujiki class manifold. But there are a simple way to construct balance manifold, just taking, that's a result by Elsa Ben, Antonella Grassi. Just take a unimodular complexly group and any left invariant Hermitian metric here. So here the complex structure is bi-invariant, and you take any left invariant metric compatible with that, that is balance. And then there is a very nice construction by Fully and Yao. The conifold transition was already mentioned in previous talk. And this in particular say that if you take the connected sum of the product of the free sphere crosses free sphere with k, connected sum k time, k bigger than or equal than 2, then you have balance metric. But this is, one doesn't know what happened for k equal to 1.
So particularly, you might think in that case that omega squared would have to represent a non-zero homology class.
Yes.
But this is an example where it
yes.
is zero.
Yes, exactly. And then there is also some nice construction due to Giussi and Podestin. And this is a non-compact simple Lie groups or inner type. And I will not say much about that, but in the same paper, they prove that they cannot have SKT. So also for this case, it's confirmed the conjecture. For the twistor space, the conjecture was confirmed by Misha. So it showed that it cannot be pluriclose. Okay, I don't want to talk about the Sol manifold case. I just mentioned that there are some classification. Probably I didn't even put all the possible classification. But this class of locally homogeneous manifold with balance metric, at least in smaller dimension, we know a lot. Not all, but we know a lot. So let's go on. And let's see the construction with Misha and Geo. Okay, before to see the construction, I want just to review a bit what is a construction that from which we start as let's say as an issue of the more general construction. The construction was done by Quinn and Wang and was the construction of 6-dimensional compact manifold. 6 is real dimension now. And these manifolds are on the same time diffeomorphic to complex Calabi-Yau. Here I mean just the canonical bundle is trivial, or morphic canonical bundle is trivial. So you have a free zero form, holomorphic free zero form on vanishing. And on the same time, there are also symplectic, diffeomorphic to symplectic Calabi-Yau manifolds. So you are very close because you have a compact complex with C10 and also symplectic on the same time. They are non-killer. So they didn't mention any, they just study topological property, for instance, the R-Lefschetz property for the symplectic manifold, but they didn't mention anything about possible metric. So what we look is okay, what we can say about Hermitian geometry there.
How did Chen get into complex dimension 3 and from, so here there's something
the complex dimension is free, yes.
Right. So how, what is its relationship to K3 though?
I will see, you will see in a moment. Okay. I will construct a diffeomorphism. Yes, we will construct as a mapping torus. You will see in a moment. So let's start with the Kummer surface. Okay, let's review the construction. we know that the Kummer surface is a smooth, compact surface that you obtain blowing up what? The singular point that you get by the complex 2 torus and just taking the quotient by the evolution, the natural evolution, that sun zeta 1, zeta 2, in minus zeta 1, minus zeta 2. You can describe also in another way, which is equivalent. You just take the blow up at any point, and then take the quotient by the evolution, will be the same. It's exactly equivalent. Okay, what I want to remark here very quickly, essentially, that the natural 2-0 form, d zeta 1 wedge d zeta 2, maybe I should use the pointer, okay, induce an nowhere vanishing 2-0 form on the torus, and then it's pulled back, essentially induce a holomorphic 2-0 form. So we have something like hyperkähler, right? Because we have Kähler plus holomorphic symplectic 2-0 form. Now it comes the construction to the 6th dimension. Let's take a matrix, 2 times 2, with coefficient d zeta plus I zeta, and we have this condition on the trace. This condition on the trace, later, we will interpret it like hyperbolicity condition, let's say, and this allows us to construct non-Kähler manifold. We'll see how. And diagonalizable. Of course, the eigenvalues are lambda and the inverse, sorry about that, I shouldn't touch this, and the inverse of lambda. And let's call the V1, the V2, the associated eigenvector on the induced map on cohomology, complex cohomology, first complex cohomology. Okay, what we have that the map is preserving the wedge of D1, wedge of D2, and also the sectional divisor, essentially. So we have a holomorphic transformation on Kummer. We preserve the induced holomorphic 2-0 form. So what we can do is, okay, taking, here, in fact, we use mapping torus combined with the product, because if you see here what we are doing, we are taking the product T2 cross R cross S1, and we are acting on P with the map A, and we are taking translation on X, and on Y we are doing nothing. Okay? So this action is standing in a natural way on an action on the product of the Kummer times R times S1, and the quotient is exactly the manifold that I mentioned before with canonical, trivial canonical bundle by essentially construction. Okay, now we set up this construction more general. So let's look at the property that you should have on your, so automorph is only holomorphic. So it's only preserving the complex structure. It's not preserving any metric, essentially, the Kähler metric, let's say. So let's take a holomorphic automorphism of a compact Kähler manifold. We say that this is hyperbolic. Essentially, if you look the induced action on the real cohomology of type 1, you have a unique eigenvalues lambda bigger than 1 will preserve essentially, and data is just the eigenvector. That's the problem. But here the property is lambda bigger than 1. That's what we are going to use. And then what we can do is do the following, like we did before, in fact. Let's take a compact Kähler manifold. Let's use a lattice in Z2 in C generated by 2 elements. And what we are going to do is the following. We use the first one element to apply our diffeomorphism F. And the second one, we don't do nothing in P. So what we will get a manifold, which is a product of a mapping torus of M under F times S1 by construction. Okay. We want to construct something which is balanced, in fact. We have something more, if you think about the Kummer construction before. And so we are asking, let's take now M, a compact hyperkähler manifold. So we have a Kähler structure and also holomorphic symplectic structure. And let's take a hyperbolic automorphism in the sense of before, preserving not only the complex structure, but the holomorphic symplectic form. This is important. What we are using essentially will be that the F is preserving the volume induced by the holomorphic symplectic form. What we show is that if you take such construction, always admit a balanced metric. I will give an idea, a very short idea. I will prove that using current. And as a consequence, the six-dimensional manifold that I mentioned before is a balanced metric. Okay, what we use for the proof, I am not going to the technical detail, but essentially we use a lot the fact that you have this projection over a complex curve, and then we just check the condition that Michelson called essential condition. So you just need to check that if you take the volume form on S1 cross S1, you do the pullback, this cannot be aptly exact. So it cannot be del of something plus the bar of something. Of course, we use also the fiber, hem, is balanced. In our case, it's stronger. It's stronger than balanced. One can apply the same construction for the real torus, but in this case, you get a Sol manifold case. Remain the problem, we have an existence condition, but remain the problem to find an explicit metric, for instance, for studying some issue related to the Strominger system or other stuff, so with a law to construct that. Here, this is much more hard to prove that our manifold is not a SKT metric. In fact, it's not only that, we can show that it cannot admit any Hermitian metric such that any power, wedge power of the Hermitian metric cannot be DD bar closed. So here we are proving that it's not SKT. I don't want to give many detail about that, just a flavor. What we use heavily is the fact, the assumption of the diffeomorphism. So the fact that F has a unique eigenvalues with lambda strictly bigger than 1, and then the action on the cohomology, 2p cohomology, has lambda p as a maximal eigenvalues. This allows, using a result by Desmailly, to construct a positive pp current such that that's the essential thing. If you apply F to sigma, then you get lambda sigma. How we use that? We use in this way. It's quite we really constructed the DDC exact, strongly positive PP current in that way. You just take your sigma, and you multiply by the power, lambda power minus t, on the product. What happened is this descends to a closed PP current on S, because it's invariant, and then just by computation, you can check that what is the alpha and what is DDC alpha. Here, what I use essentially is that this IDT is the one form on S1, on the factor S1, and that allows us to conclude that you have a strongly positive PP current, essentially, with the other part. Okay, let's go to the second part. Okay, we saw before, complex surface cannot be balanced unless they are Kähler. Here, the situation is completely different by a result by Gudjon, because Gudjon proved more general. If we take a compact Hermitian manifold of complex dimension n, then you have a unique function such that if here you just work in the conformal class of your Hermitian metric. So if you take the exponential of your function times omega, and you take the wedge n minus 1 time, this is DD bar closed. And the other condition is just the integrability condition that ensures that the solution is unique. But what we use here essentially that for n equal to 2, if you take a complex surface, always, and you take any Hermitian metric in the conformal class of your metric, you always have a SKT metric. So it's completely different than before. That's the result. We can give another interpretation of the SKT metric This is in terms of the bismuth or Strominger connection. We will see later how the torsion of this connection, the case of the bismuth connection as a role. This is again Goduchon theorem. It shows that given a Hermitian manifold, you have an affine line, a canonical Hermitian connection, so connection preserving the complex structure and the metric, and they are characterized by the torsion. In particular, you have the Chern connection that essentially one can see that's the connection for which the torsion is trivial, one component, and the bismuth connection, for which is free form. And that is how it comes the name Stone-Keller with torsion. Everything is determined uniquely by the torsion. What is the torsion from the case of the bismuth connection is given by -1/2 dc of omega, our free form. So the condition to be SKT is equivalent to ask that the bismuth torsion connection is closed. Example. The more natural example are the Samuelson spaces. So we consider a product of a simply connected compact semisimple group times an abelian group, K. Of course, it should be even, the product, even dimension, the product. And let's say J a left invariant complex structure compatible with a bi-invariant metric there. So in this case, it turns out that the torsion is quite simple. It's just a Cartan free form. It's just given by the bracket. And so it's closed. But nabla, in this case, nabla, the bismuth connection is flat. Okay, one can look in general for flat, for a Hermitian metric for which the bismuth connection is flat, and you don't go so far from that example. There is a result by Wang, Yang, and Zheng, proved in 2020, that is say essentially up to a finite cover, in the compact case, if you look for a compact bismuth flat Hermitian manifold, then you go back to the product of the compact semisimple group time a torus. That are the only, here I say local, because you can apply also some isometry, group of isometry. So up to that, you go there. Okay. Non-bismuth flat is quite rich. The literature now, most of the cases are in fact locally homogeneous examples. So Neal manifold, Sol manifold, I mentioned some of the names, probably I forgot some. I apologize for that. But there are also locally homogeneous construction. One is due by the two brothers Grantcharov and Yatsampon. And this is the connected sum of product of S2 cross S4, K minus 1 times, connected sum with the product of S3 cross S3. Many of the examples, for instance, the Neal manifold case, are in fact torus bundle over some Kähler manifold. In that case, over torus. In this case, in the second construction that I mentioned, is again a torus bundle over Kähler. So many examples are like that. So that's the first thing about SKT, the known example. There is a more general construction due to Poder and Thakur, I mentioned, where they construct SKT metric on a total space of principal bundle over projective manifold, and with special type of structure group, and they have additional condition on the characteristic class that there I didn't put, but that's the idea. But essentially, they generalize the previous construction. Okay. We combine the SKT condition with the Calabi-Yau with torsion condition that is quite natural. It's like to have a generalization of the Kähler Calabi-Yau, let's say, but using the bismuth connection instead of the Levi-Civita connection. We say that the Hermitian manifold is Calabi-Yau with torsion, CYT, if the natural Ricci form that you can construct using the bismuth connection, so you take a local orthonormal frame here, EI, and you just take essentially the trace in that way using J. If this Ricci-Bismuth form vanishing, then since it represents the first chain class, then you have the first chain class of your complex manifold vanishing. And also you have a restriction on the holonomy, restricted holonomy of the Bismuth connection, because it should be contained in the special unitary group SUN. Okay. Why? I don't want to talk about flow here, but I want to say a link with the pluriclose flow. So when you start with a complex manifold, and you take a starting metric, let's call G0 with fundamental form omega 0, which is SKT, Street and Tian introduce a geometric flow which evolves the metric, preserving the SKT condition, the D bar closure. And the idea is similar to the usual Ricci flow, because the only difference here that, of course, if you take the Ricci form of the Bismuth connection, this is not a type 1-1. So you consider the type, the part 1-1 of the Bismuth Ricci form, and you evolve in that way. There is, it was that condition that I mentioned later. So essentially, it's just, one can ask for static thing, right? When the Bismuth, the Ricci, the Bismuth connection, the power 1-1 is proportional to the metric. And the case, when you have SKT plus Calabi-Yau with torsion, is exactly the case when you have that condition for lambda equal to 0. There are very nice properties of this metric, are studied by Mario Garcia Fernandez and Streets. They study a lot, and they also ask the question, can you have such type of metric, which are SKT and Bismuth Ricci flat, but not flat? We know now that there are examples. Okay, trivial example, let's say, are Kähler-Ricci flat, in that case the torsion is 0, Bismuth flat, the Samuelson space that we saw before, or product of that. So the idea was to use some type of construction using, again, the mapping torus to arrive to metrics which are SKT and Calabi-Yau with torsion, but not Bismuth flat. One thing that one can look is in the class homogeneous case, that's the first thing that one can look. In the because there is a result by Georg Lancherov for compact complex homogeneous space. We see 1-0, of course, you need that. And it shows that, in fact, after you do a deformation of the complex structure, you have a homogeneous Calabi-Yau torsion metric if it has an invariant volume form, invariant the action of the transitive group. So the question is, okay, in this case, what happened for homogeneous case, that type, since many of these examples have non-zero Bismuth curvature? Now we know that it's not possible. This was previously with Geo and Luigi Vezzoni. We look in the non-Kähler class of C-space. So we have compact complex manifold with a transitive action of a company group we touched by B holomorphism, and we find a fundamental group. We have a characterization by 1. We know that there is a transitive action of a compact semi-simple group, and we show, in fact, that you don't go far from the product, because the only case that you get is a product of a company group and a Kähler manifold, compact Kähler homogeneous manifold, a generalized flat manifold. And the way I will prove is internally topological. We use an abstraction by Cavalcanti. They show if you have a compact complex manifold for which the odd number H30 is 0 and H1 is also 0, then it has to have a symplectic form. And that's exactly how we show our result, because we prove first that H30 is 0, And for the other, we can prove that H1 is non-zero only if up to a final cover, you have something like a product of a compact group and another non-Kähler space. And then you reduce again, and you go to the product of a compact Lie group and generalized Fleck manifold. Now we know from essentially the last result that I mentioned by Barbara, it completes what we start to look with Geo. Okay, in semi-simple case, now we know the answer that you cannot have such non-bismuth flat metric, which are SKT and Calabi-Yau torsion. We don't know about the compact case. It's still open. How we get the result? We first show if you have a compact semi-simple group and you have a left invariant complex structure, if you have an SKT metric, which is compatible with the complex structure, left invariant, then it has to be compatible with bi-invariant metric. And then under the assumption of being also invariant under the action of the maximal torus, because when you have your left invariant complex structure, essentially you have a choice of a compact torus T. We show that in fact you go essentially to the bi-invariant metric, so it's bismuth flat. Very recently, in a very nice paper, Barbaro improved our result, removing the condition that is invariant under the T action. And it's very nice. I just mentioned the proof, not the proof, but I mentioned that he used the result about pluriclose, the stability of pluriclose flow that I mentioned before, when you start with a manifold which is bismuth flat, Hermitian and bismuth flat. So the flow has a role in that. It would be nice to have a proof also not using a flow, but that's right. So let's see now. I have the last 40 minutes. I am on time, right? Yes. With the construction. Okay, we have some example, non-bismuth flat. Okay, they are nice, but we'll see at the end that they have a condition that would like to remove. But anyway, let's start. There is a nice result by Ferreira, Agricola, Ferreira, and Friedrich, where they study the condition in general, not in the Hermitian case, just for a Riemannian manifold, and then you have a connection, a metric connection with torsion in the simply connected case, and the torsion is close and parallel, and you have that result. Here the idea is to look what happened in the Hermitian case. So let's take a compact bismuth Hermitian Einstein manifold. If you don't like the name, it just means that the metric is SKT and Calabi-Yau torsion. And such that the torsion is parallel. The bismuth torsion is parallel with respect to the bismuth connection. Okay, you get, essentially, then we can show that the Riemannian holomorphic universal cover is just a product, not only as a complex manifold and as a metric, to essentially a Kähler-Ricci flat manifold and a bismuth flat open complex submanifold of a Samuelson space. So you go back to the product. Okay, in the Kähler case, the proof, of course, is trivial. Let's see what happened in the non-Kähler case. The proof is in two steps. Essentially, what we use is the kernel of the free form, of the bismuth torsion free form. Looking at, essentially, we are able, using the fact that the torsion is parallel with respect to the bismuth connection, to split the tangent bundle in two orthogonal, the direct sum, or two orthogonal parallel subbundle, which are preserved by the complex structure. In fact, are preserved posteriori by the Levi-Civita connection and by the bismuth connection. One of the two is a subdistribution of the kernel. To make that, we use a sort of maximality with respect to the I invariance. And the other distribution, F2, doesn't contain any subdistribution corresponding to a Kähler-de Rham factor. This will be essential to conclude for the second step. Because then, of course, what you can do is to go to universal cover, to lift your structure on the universal cover. Then by the de Rham splitting theorem, you can show, in fact, that you have your universal cover is a product of what? One, the first factor M1 is Kähler-Ricci flat. That comes from the fact that they correspond to F1, essentially, which is in the kernel of the torsion, of the bismuth connection. And the second factor is, in fact, that correspond to an open submanifold of the Summerson space, is related to the fact that F2 does not contain any subdistribution corresponding to a Kähler-de Rham factor. And then here we use a characterization by Zhao and Zhang to conclude that essentially you go to the Summerson space. So when you impose these two conditions, the extra condition, let's say, that the torsion is parallel, you have a control about the universal cover. And the manifold that we are constructing, more manifold, the construction that we are looking is something that has a universal cover of this type, but is not the product. How we get that? This is the joint work with Brienza and Grancher and Gale. So let's start with a compact Kähler manifold, and let's take a Kähler isometry. Then the mapping torus emits a natural SKT structure, and if G is non-Ricci, is non-flat, Ricci flat, then we get an example which is bismuth Hermitian Einstein with non-flat bismuth connection. In particular, the torsion is parallel with respect to the bismuth connection. One can check essentially checking that the curvature satisfies the first Bianchi identity and the structure is SKT. That imply that condition. How we construct that? Essentially, we use the off-surface construction. We combine the construction related to off-surface with the diffeomorphism in that way. We take the product of the Kähler manifold times C2, where you remove the origin, the 0, 0. And we just say the product complex structure, J times J minus. J minus is a standard complex structure on C2, on the universal cover, let's say, of the off. And then we take this action here of the integer. You just take the power of C, and then you take the power 2 power n on the second factor. What happened that that's nice because one can show that the quotient is in fact diffeomorphic to the mapping torus that I mentioned before, was something related to the Kähler, one factor, and the other the identity on S3. And this form, this natural form, is preserved by the zeta action and then descend to SKT metric, let's say. Okay, what we can say about the manifold? The first thing that we can say that the manifold is in fact a fibration over the off, essentially with fiber a Kähler manifold. And from that, since you have a proper holomorphic map over a manifold which is non-Kähler, you can show, using Michelson result, if you like, that it cannot emit any balance matrix. So again, we have SKT and non-balance. Another thing that one can show is that the manifold, the topology of the manifold is a product essentially of a mapping torus of a Kähler manifold and a free sphere. So what we have that is formal in the sense of Sullivan because it's a product of two formal manifold. The result about the formality of a mapping torus of a Kähler manifold was proved by Chinea, De Leon, and Marrero, if I am not wrong. But, nice thing, the first Betti number is odd. Here you can internally describe the cohomology of your mapping torus, and you can show that it's 1 plus one part that is always even dimension that is coming from the Kähler, essentially, thing. So it doesn't emit any Kähler metric. Okay, I finish showing an example, a concrete example that you have, because, okay, if you start with torus, then you get something flat. But let's take the case of a K-free surface with Ricci flat Kähler metric. If you take a Kähler isometry of your K-free surface, different from the identity, and then you apply the construction that we saw before. So you take K, your K-free surface, you take the Frisch field, and then you take the diffeomorphic, which is a combination of let's say the Kähler isometry and identity on the other. We know that is bismuth Hermitian iso because it's SKT, and the bismuth connection is non-flat, but Ricci bismuth flat. Okay, one can say, okay, maybe you just take the product, right? You're just working on the product of something which is Kähler and the off, essentially. But this is not possible because by, again, computing the cohomology of your mapping torus, you can show that, in fact, the second Betti number of the manifold that you construct in that way is smaller than the second Betti number of the product. So it's not really product. It's even not locally homogeneous, as example. So this provides, first, I say non-trivial example of Kampa-Bismuth Hermitian manifold, but again, the universal, okay, it's not trivial, but the universal cover in some sense is trivial, right? Because it's a product of something which is Kähler times something which is bismuth flat. But it's not that. It's not biolomorphic to that. It's really different. So now the question, okay, there are two questions. There was a question already before, maybe it was more simple to ask, okay, just take a Kompany group of even dimension and see if you can have something which is symmetric, compatible with a left invariant structure, which is Calabi-Yau with torsion SKT and non-bismuth flat. This is still open in the non-semi-simple case. It seems to be hard to study because you have no control in the abelian. In the abelian part, it's harder to have a control. You need control on that.
So
yes.
The psi here, I guess the point must be that it's non-trivial on second cohomology, right?
Yes.
But maybe if you wanted to make it really concrete so people didn't worry about that, you could just say, suppose your K3 is a double cover of an equate surface and let psi be the non-trivial transformation.
Oh, yes, yes, that's another way. Yes, yes. Of course, here the bismuth torsion is parallel. So the thing is, can we have some example which is non-parallel in some way? Maybe not, who knows? Even in the Kompany group case, you probably, what I do not know even, if only the condition compact, I mean, the problem that here, all the time, the cohomology is something that you don't know in general. For instance, in Barbaro result, he computed the Eppli cohomology. So using the Eppli cohomology as information. But in general, it's not clear what type of restriction you have combining with the two conditions. Calabi-Yau, torsion, and what I did. Oh, I went back. I think I will finish 1 minute before. You will not complain for sure. Thank you very much for your attention.